Welcome to The Deep Dive. We're going to explore something today that you probably see constantly, but maybe don't think much about. We're looking at what keeps things like utility poles standing tall. It's all about, well, guying and anchoring. These are kind of the unsung heroes of structural support.
Yeah, and our guide for this journey is a technical document, Guying Anchors RUS.pdf. It's, full of engineering details,
Yeah.
the real nitty-gritty, exactly. And our mission, really, is to pull out the key insights from this technical stuff. We want to help you appreciate the surprising precision behind it all. It might seem simple, but it's definitely not. So let's start right there. These guys, what exactly are we talking about when we use that term in engineering, and, why are they so critical for keeping a pole upright?
It's a great starting point because, yeah, guy sounds pretty informal, but in this world, they're absolutely vital. Essentially, think of them as high-strength tension cables. Their job is to counteract forces acting on the pole. Things like, heavy wind or maybe the constant pull from the electrical lines stretching out.
Ah, okay. So without them, the pole is just sort of vulnerable.
Exactly. It'd be much more likely to lean or even fall over. And what's really interesting is how varied they are. It's not just one type of cable.
Right. You're saying there's a whole toolkit just for guy wires.
Precisely. The source document in Index E, it lists out different guying assembly units. You've got the basic single-down guy. That's the one going from the pole down to the ground. And even that comes in different types, like a through-bolt type, which actually goes through the pole, or a wrapped type, where the cable wraps around it.
Okay.
Then there's the single overhead guy, again, usually a through-bolt type, used maybe between poles or for different support needs. And it gets even more specialized. When you have poles holding multiple heavy lines, you need things called guy guides.
Guy guides, what do they do?
They manage multiple guys attached to the same pole, keep them spaced correctly. You can have a single-down guy guide heavy-duty or something much bigger like a four-down guy guide large conductors, pole band type.
Wow. 4 guys. That implies some serious forces involved. Huge forces. And there's even a guy strain insulator guide. That's a safety feature, basically, to stop electricity from traveling down the guy wire if something goes wrong.
That's way more detailed than I imagined. And I assume these aren't just like best practices. The construction specifications sound pretty firm.
Oh, there are definitely rules, hard rules. And one of the big ones, maybe not obvious, is timing. Guys must be installed before you put the conductors up.
Before the heavy wires go on. Why is that?
Think about it. You need the support system in place before you add the load. Putting heavy conductors on an unsupported pole during construction, that's asking for trouble. It maintains stability throughout the whole process.
Okay, that makes perfect sense. Build the support first. What else?
Well, there's the grade of construction, basically the strength rating of the guy system. It has to be at least as strong as the pole itself, or as strong as the highest grade conductor it's supporting.
So the support needs to be equal to or better than the thing it's holding up.
Exactly. It ensures the whole system is balanced in terms of strength. You can't have a weak link.
And what about where they're placed? Is it just attach a wire, or is the angle critical? Like in tug-of-war, you pull straight back right.
That's a really good analogy. Alignment is absolutely key. For what they call dead-end structures, where the lines stop at that pole, the guys must be in line with the pull of conductors as nearly as practical.
Pulling straight against the force.
Precisely. And if the pole is at an angle where the line turns, you use bisector guys. And these need to be placed, again, as nearly as practical to the true bisector of the line angle.
So splitting the angle perfectly in half with the guy wire.
That's the goal, yeah. To balance those sideways forces efficiently. It's all geometry and physics in action.
Okay, this next part really caught my eye. The specific recommendation for a 1.1 slope for guy leads, particularly on dead ends, and the warning that minimum guy leads are not recommended. What does that 1.1 slope actually mean for stability? Why is it better?
Right. That 1.1 slope is sort of the gold standard for efficiency. Think of a right-angled triangle formed by the pole, the ground, and the guy wire. A 1.1 slope means the horizontal distance out from the pole to the anchor point is equal to the vertical distance up the pole where the guy attaches. It's essentially a 45-degree angle.
Okay, equal distance out and up. Why 45 degrees?
Because that angle is extremely effective at translating the horizontal pull on the pole from wind or lines into downward tension that the anchor can handle. It directs the force optimally into the ground.
And what happens if the lead is too short? A minimum guy lead? That means the anchor is really close to the pole, right?
Exactly. And that makes the guy wire much steeper, more vertical. Think about pushing something heavy. pushing horizontally is effective, pushing almost straight down, not so much for moving it sideways.
Ah, I see. So a steep guy wire isn't really pulling against the horizontal force effectively?
Right. It puts way more vertical compression force down onto the anchor and the pull base, and it's much less efficient at counteracting that sideways pull that wants to bend or break the pole. It's just not good engineering practice if you can avoid it.
And this ties into safety factors, I bet. The document mentions something crucial here.
Yes, absolutely critical. It states, the applicable NESC safety factors have not been, but must be applied to determine the allowable guy wire tension.
NESC, that's the National Electrical Safety Code.
Correct. It's the standard. These safety factors are basically multipliers you apply in the design calculations. They ensure the system can handle loads far greater than what's normally expected. It builds in a huge safety margin.
So they're not optional suggestions. They must be applied.
Non-negotiable. Skipping them means you're designing right up to the expected load with no buffer for extreme weather, unexpected stress, or material degradation over time. It's fundamentally unsafe.
Okay, wow. So the guys are precisely designed, angled, and tensioned. But they need something solid to pull against, down at ground level. That brings us to anchors, right? What's the hidden story there beneath the surface?
Exactly. The anchors are the other half of the equation. They're the connection point in the earth, the foundation that resists all that tension from the guy wires. You never see them once they're installed, but their holding power is paramount.
Like the roots of a tree, almost.
It's a good way to think about it, yeah. They transfer that massive pull deep into the ground. A perfect guy wire is useless if the anchor slips or pulls out.
And just like guys, I assume there isn't just one type of anchor.
Definitely not. Index F in the source lists various anchor assembly units. There are expanding type anchors, which mechanically open up underground to grip more soil, really effective in many conditions. You also have screw anchors, which look like giant screws. These are often power installed with hydraulic equipment. Very common now.
Power installed, okay. Faster, I guess.
Faster and often provides more consistent holding power because the installation force can be monitored. Then you have things like plate-type anchors, basically a flat plate buried deep, and for solid rock anchors, which are grouted or expanded directly into drilled holes in the rock. And for really difficult ground, like swamps or bogs, there are specialized swamp anchors, often power-installed screw types, designed to reach deeper, firmer soil layers through the muck.
So an anchor for every occasion, basically. It sounds like putting them in correctly is just as important as picking the right one. What are the key rules there?
Absolutely critical. The construction specifications for anchoring are just as detailed. First off, the anchor rod itself must be in line with the strain.
Meaning pointing directly at the guy wire connection up on the pole?
Yes. So the pole is straight along the rod, maximizing its efficiency, no awkward side loading. Then there's a neat little detail. How much rod sticks out? Usually approximately 6 inches of the rod remains out of the ground, just enough to connect the guy easily.
But there's an exception.
Right. In cultivated fields where farmers might plow, you're allowed a maximum of 12 inches sticking out. This gives it a bit more clearance so it doesn't get buried or snagged by equipment. A small thing, but operationally important.
Makes sense. And what about the hole you dig?
The backfill is crucial. The specification says, the backfill of all anchor holes must be thoroughly tamped the full depth. You can't just shovel the dirt back in loosely.
Why tamp it so carefully?
Compaction. Tamping compacts the soil tightly around the anchor, maximizing friction and the soil's resistance to the anchor pulling out. It develops the anchor's full holding power. Loose soil just won't hold as well. And some anchors, like cone anchors, have even more specific instructions. You backfill with coarse crushed rock for 2 feet above the anchor and tamped, then finish with tamped earth. That rock provides excellent drainage and stability right around the anchor head.
Okay. And the fundamental principle behind all this?
It boils down to this. The maximum load with overload factors transferred to the anchor should not exceed the designated maximum holding power. Basically, the engineered load, including those NESC safety factors, can't be more than what the anchor is rated to hold.
And that rating, it depends on the anchor itself and, crucially, the ground it's in.
Exactly. And typically, the standard anchor ratings you see are coordinated with the maximum holding power of average Class 5 soil conditions, which leads us right into the ground itself.
Right, Class 5 soil, the average baseline. But, the ground isn't always average, is it? What happens when you hit something softer or looser? This feels like where the anchor meets the mud, so to speak.
That's the perfect way to put it. Soil quality is a massive variable. It dramatically affects how well an anchor holds. The rule is clear. When the anchor is used in poorer soils, the holding power of the anchor should be derated.
Derated, meaning you have to assume it won't hold as much.
Precisely. You have to reduce its rated capacity in your design calculations. It's not just a suggestion, it's essential for safety. You can't expect an anchor to perform the same in, say, hard clay versus soft, silty stuff. Engineering has to account for this natural variability.
Does the source give guidance on how much to derate?
It does. It provides a suggested guide, which is pretty standard practice. Derate by 25% in Class 6 soil and by 50% in Class 7 soil.
50%. That's having the anchor's strength just because of the soil type.
It is, and it shows how critical understanding the soil is. A 10,000-pound anchor in Class 5 soil might only be trusted for 5,000 pounds in Class 7. That completely changes your design.
And what about the really bad stuff, Class 8 soil?
For Class 8, yeah, you usually need those special anchors we mentioned, swamp anchors or power-driven screw anchors. The idea is to bypass the really poor surface layer and get down into something firmer below. It's also worth mentioning the document notes that log-type anchors are acceptable for use on distribution systems, but points to another RUS bulletin for the specifics on those. They're an older style, perhaps less common now, but still potentially usable.
So this classification system for soil is obviously really important. Can you give us a quick rundown? What makes a Class 0 different from a Class 8? It sounds like the ground itself is a key engineering material here.
It absolutely is, and the descriptions in Table F are quite specific. It's a spectrum of soil strength and composition. At the top you have Class 0, sound, hard rock, unweathered. That's bedrock, the best possible foundation you could ask for.
The dream scenario.
Pretty much. Then classes 1 through 4 cover progressively less dense but still very competent materials. Things like very dense and ore cemented sands, very hard silts and clays, down to dense clayed sand and gravel, and medium dense sandy gravel, all generally good stuff to anchor into.
Okay, call it ground.
Then we hit Class 5, our baseline average, medium dense coarse sand and sandy gravels, stiff to very stiff silts and clays. This is what standard anchor ratings are often based on.
Got it, the benchmark.
Now we get into the poorer soils needing degrading. Class 6 includes things like loose to medium dense fine to coarse sand and firm to stiff clays, getting weaker. Class 7 is where you really see the drop-off. Loose fine sand, alluvium, low west, soft firm clays, much less holding capacity here, hence that 50% degrading.
Right, soft and loose.
And finally, Class 8 is the most challenging. Peat, organic silts, inundated silts, fly ash. Very soft, often waterlogged, very low strength, needs those special anchoring solutions.
Wow. So what this really means for you, listening right now, is that the ground under your feet, it's not just dirt. It's a complex, classified engineering environment. Its properties directly control how we keep critical infrastructure standing. It's this invisible dance happening between steel, tension, and the earth itself. It really is incredible. We've gone from the basic idea of a guy wire to specific angles, mandatory safety codes, different anchor types for every conceivable ground condition, and even a detailed soil classification system, all working together silently.
It's a whole system, absolutely. And understanding these details, even the ones completely hidden from view, like the anchor type or the soil class, helps appreciate just how robust and carefully designed our infrastructure has to be.
Every little piece matters. That 1.1 slope, the tamped backfill, the NESC factors.
Exactly. Each specification is there for a reason, contributing to the overall resilience. It's about ensuring stability and safety against considerable forces day in and day out. It's quite an achievement of applied engineering.
So here's something to think about. Next time you walk past a utility pole, or maybe any tall structure with visible supports, pause for a second. Consider that invisible engineering holding it up. Think about the angle of those wires, the anchor buried deep below, and maybe even the type of soil it's gripping onto. What other hidden foundational systems in our daily lives do you think are engineered with this level of precision, reacting constantly to the very ground beneath our feet?